Hi guys, today we're looking at a planimeter. I was watching a YouTube video of a gentleman designing a sailboat. The YouTube video was called The Elegance and Joy of Wooden Pond Yachts. In other words, radio-controlled sailboats. He used a planimeter, P-L-A-I-N-M-E-T-E-R, to calculate the area of a frame. Here's one I ordered on eBay. I got this for $20. Came in a box that's in pretty good shape. I had to tape one of the edges. It was advertised as new, and that's a relatively simple polar planimeter. When I watched the video, I was flabbergasted. I thought, how can that be possible? This device traces a curve with a needle point connected to a measuring wheel, and it converts the length of the tracing to the result of an integral function. In other words, the area of the shape, which, if you know a little bit about calculus, and I just know very little about calculus, integration is the area under a curve, and this is basically giving you the integration of a function without knowing the formula for that function. Pretty much magic. This is a polar planimeter with a zero setting device. Like I say, it cost me $20 on eBay, $15 plus $5 shipping. These are worth about $30. They vary in price from $20 to $200 or $300 or $400, depending on how fancy you want to get. And this one's in very good condition. These were invented by Johann Martin Hermann, and he didn't actually build the first planimeter, he invented the concept. The Swiss mathematician Jacob Amsler built the first modern polar planimeter, and many developments followed his famous planimeter. He sold thousands of them. So I'll take this out of the box. We only need two components here. That's the anchor arm, and this is the tracing arm. There's an extra screwdriver for the adjustment of the vernier caliper, and an Allen screw to get at things, and an extra sharp point that could be replaced on the end of this one if it ever gets broken or dulled. So in its simplest form, you anchor the point someplace, and then you put the pivot point in there, and then whatever you trace, it will give you the area of the surface you trace. And this is doing a 1-to-1 inches ratio, and it has a reset button here. So I'll reset this. If I put the point there on the beginning of that little 1-inch square, and then if I move the point clockwise around a circle, in this case a square, and of course the more accurate you are, the more accurate the reading will be. And then in this case, it says 1. Actually, it says 1.5. Well, actually it says 1.05. Now if I can put it any place around here. If I start it here, again, I'll reset it. Get a good reset. If I trace 4 of those squares, I should get 4 square inches. Let me reset that and try again. And perhaps my anchor point moved. So I'll try 4 square again. And now I'm reading 4.01. So it's pretty accurate. And the amazing thing is that it can do anything. It doesn't have to be a square. So for instance, I'll get a piece of paper here. I'll tape it down so it doesn't move. And if I draw a 1 inch or make it a 2 inch, two-inch radius circle with my cheap compass, and we'll see what we come up with for square inches. Now, when you're setting this up, you try to get roughly in the center of the shape you're doing. It doesn't matter if it's exact center, and make this at a right angle and push it in so the pin inserts and stays put. The idea is to get the maximum range of movement of this arm. So if we reset this, whoops, you have to have a starting point and an ending point. I'll make a starting point here. Doesn't matter where you start as long as you go clockwise. I get a good reset. And then we trace. And when you get to the end, it says that the area of that circle is 1, 2, 8, 7. And when I did pi r squared, I came up with 12.56. So we're close. You get the idea. Now, what would be more difficult is if you had another circle superimposed and you didn't care about adding the 2 circles, but you want to know what the total area of those 2 circles was. Again, I can reset this counter and start tracing the outline of this shape. And of course, the faster I go and the sloppier I go, the less accurate it is. I'm exceeding the length of the thing. I should have put that circle higher. Now, according to my planometer, this circle in the center says 3. So it's 3, 3, 8, 2. Which is, of course, not even close to the correct answer. I did this exercise again off camera, and I came up with 22.6 square inches for these 2 circles combined. Now, if you were working from a map, and these were originally used as drawing aids and also as for map makers, so if they wanted to know the area of a lake and they had a top-down picture of a lake, an aerial photograph, or even walked around and measured the outside measurements of it relative to some position, then they could use the planometer to determine the area of a lake, and they could express it in acres or whatever factor they want. So to scale this, since this has a 1-to-1 scale of inches, if you were measuring a map that was 50 feet equals 1 inch, then you would take 50 times 50 which is 2,500. So whatever your planometer said it was in square inches, you would multiply it by 2,500 and you would get 34,400 square feet. Now there are several types of planometers. This is a very simple one. This was made in the 1950s and 60s. They made thousands of them. This is a polar planometer, and sometimes called an Amsler planometer. He was the guy that invented this style planometer. Before this was the linear planometer. There's also compensating polar planometers, and the only difference is this bar here is adjustable from side to side, and there will be a chart of scales to set up so that you can get correct scales. There's a dot planometer, which is basically using graph paper to determine the area of a circle. So if you had a series of dots, all say 1 centimeter apart, and you had it across the entire device, you could just count the dots and determine the square area. There's a Pratt's or a hatchet planometer. Sometimes some variants are called spoon planometers, and that uses just one arm and a complex movement, and you can simulate that with a long spoon. And there's new digital planometers, and one really complex one, which isn't used anymore because they're too complex, is the Ernst-Planimeter. And I haven't seen one, but there's orthogonal planometers. And one really interesting one is radial thermometers, which you put the planometer inside the circle and you measure around in a circle, and it gives you the average radius of the circle, which you could argue what good is that. And it's really used for circular plots of things like temperature changes or density changes or atmospheric changes over periods of time. There's examples of all of these on YouTube and on the internet, and I'll save a whole bunch of links in the bottom to describe them. So what happens if you turn it counterclockwise? Well, let's try it and see. So for instance, let me reset this. I'll try to measure 1 square inch right here. But instead of going clockwise, I'll go counterclockwise. And I came up with 9, which is probably -1 from the 10th decimal. So it really went backwards. Let me try 4 square inches. I'll reset it again. Right at this point. I did that wrong. I didn't draw 4 square inches, I drew 2. Let me do it again. And that came out to 6, which again is probably 10 minus 4. It's a marvelous device. Now, one of the uses, and the original use that I got interested in, was watching this guy design a boat. Now, let me get this piece of paper off here. And in case you're wondering about any of this magic, underneath this thing, there's just one wheel. So the only way it can sense angular motion is by the fact that there's an anchor point here, and if you move it this way, the wheel turns. But if you go sideways, you actually drag the wing thing sideways, and it doesn't change at all unless you go up and around. Very strange. So if you were designing a boat, and here's a hull, frame diagrams, and this is for a little sailboat. And this is sort of typical, and this is from a set of plans for a full-scale 19-foot sailboat. In fact, this sailboat, called a Wild Duck. I built a model of this. But the first model boat I ever built was a model tugboat, and it was 4 feet long. And when I got it to the stage where it could hold water, I put it in our jacuzzi and I added weight to it to determine how much weight I had to add to bring the tugboat down to the water line. And I was kind of shocked because it took 40 pounds of weight to get the boat down to the water line. So there's a lesson to be learned here. If you don't want a boat that's too heavy to pick up and carry to get to the lake, or that's so light that it'll just blow over, you really need to know the displacement before you start designing it. So here's the frames for a model Wild Duck. I'll show a picture of a real one. And they mirror these, so here's frames 1, 2, 3, 4, and 5, and it's really half a frame. And here's frames 6, 7, 8, 9 going that way. So here's the water line. I should draw that. I need a straight edge. Any straight edge will do. So what you care about on displacement of a boat is the area that goes, you want to know about the volume from the water line down to the bottom of the boat. So you'll notice for frame 1, everything at frame 1 on this boat and frame 10 on the back of the boat is actually above the water line, so we don't care about that. But this frame, this little triangle actually, would be one thing that you care about the area of, and each frame gets bigger. So if we take the biggest frame on the boat, which is frame 5, we would measure that as follows. I'll zero this. And trace the outside circumference. Of frame 5. And that would be 2, 2, 3. So that was 2.23 square inches. Now that's half a frame, so you would double that to 4.46 square inches for frame 5. Now if you likewise measured frame 4's area, which would be something less, and then you added those two together and divided by 2, you'd get the average frame size between the two. If you had a lot of frames, taking averages would work out really well. So then you take all of those averages of the areas between each frame, multiply each frame's average size times the distance between frames, and add them together, and then scale by whatever the scale factor that you're trying to use is for the size of the boat, because it's probably not inches, although you could print out frames for a model boat in full scale, in which case this would have worked if this was full scale. And in fact, for the wild duck, that's probably pretty close to full scale, but I just randomly printed this size. You added all that together and then take the weight of water, and you know the displacement of the boat, and you know whether it's too light or too heavy, if you can build a bigger boat if you'd like, and change the size. Pretty cool. So that's it. I'll leave a bunch of links below. One of them shows planometers made out of a Lego set. One of them shows a planometer made out of a beer can. The ones by Chris Staecker, they're the best ones if you care about the technical details of a planometer and you want really good information. So there's a lot of information on the internet about these magical little devices. And part of the inaccuracies I'm getting here is this is a fairly slick surface. You want a nice porous surface like a drawing table. It doesn't roll that well on this surface, especially when I scoot over here and hit the edge and stuff. But in its environment, these are very accurate, and people who use them professionally would take multiple measurements and get the average of their measurement between them to get an accurate reading. And in most cases, because you have 4-digit accuracy, it was as accurate as you could calculate at the time. Ironically, the calculation for how planometers work didn't happen until Green's theorem proved that planometers work mathematically, and that was almost 100 years later, 1947, when Green's theorem proved how planometers actually work. So that's it, guys. Thanks for watching, and I hope you enjoyed the video.